So in this problem, we have a small bead of mass little m, which can slide without friction along a horizontal wire. It is attached to two springs, both with spring constant K, and the other endpoints of the springs are kept fixed. So when the springs are unstretched, their equilibrium length are both L0. And we're asked to find in part A of the problem the net force on the bead as a function of x. So let's start off by drawing an isolation diagram of the bead. So the two forces acting on the bead are going to be the two spring forces of the springs that are attached to the bead. So we've got the upper spring, which is going to exert a spring force according to Hooke's law that has magnitude K times delta L, where delta L is going to be the stretch of the spring from its equilibrium length. Now, this force is going to act on the bead at some angle theta with respect to the horizontal, and the lower spring is going to act with the same force, K delta L, at the same angle theta with respect to the horizontal in the opposite direction, since the two springs have the same spring constant and the same equilibrium length. So notice that by symmetry, the vertical components of the forces cancel, so the net force is just going to be in the horizontal direction. So we can write, using Newton's second law, that the net force in the x direction is going to be the sum of the horizontal components of the spring forces, which is going to be 2 times K delta L cosine theta. And since this is a restoring force, then we have to add a negative sign to indicate that the net force acts opposite the direction of the position of the bead. So now we just have to figure out what delta L is and what theta is. So if we let L be the length of the stretched spring, then delta L is just going to be equal to L minus L0. And similarly, by geometry, cosine theta is just going to be given by the adjacent side, which is x, over the hypotenuse, which is L. Thus, it's going to be x over L. Now, L, using Pythagorean's theorem, is just going to be the square root of the hypotenuse, or sorry, not the hypotenuse. So you make the square root of L0 squared plus x squared. So that's just using the Pythagorean theorem, where a squared plus b squared is equal to c squared. So we get that net force, F net, is equal to negative 2k delta L, which is L minus L0, times cosine of theta, which is x over L. So now if we bring this inside the parentheses, we get negative 2k times, we're going to factor out the x, L over L minus L0 over L. So L over L is 1. And now we substitute in our value for L, which is the square root of L0 squared plus x squared. Now notice that we can factor out a factor of L0 from the square root side. So that would leave us with negative 2kx times 1 minus, and the L0's will cancel, so we get 1 over square root of 1 plus x squared over L0 squared. So that just simplifies to negative 2 times kx times, in brackets, 1 minus, in brackets, 1 plus x squared over L naught squared to the negative 1/2, which is our final answer for the net force on the bead as a function of x.